Hello folks, welcome to the second episode of quantum computing. In the first episode, we discussed the first postulate of quantum mechanics, which is that of superposition. Recall that the principle of superposition states that any quantum system, ket psi, can be written as the superposition of two quantum states, say 0 and 1, and some amount, some linear combination of both of these states. Today we're diving into the second postulate, and that is measurement. Measurement is the most important thing in quantum mechanics. Measuring a qubit destroys it, makes it from something quantum to something classical, and today we're going to dive all into the nuances of measurement. So let's go ahead, get started. Before I begin, we have a special message from someone you might know. Tom? Hey there folks, Tom here. Welcome to Quantum Computing Lecture 2. I hope you enjoy it. Begin by discussing projections, and then we'll discuss polarizers, and then finally operators, and then we'll move on to measurements, and then the different kinds of measurements, such as one-dimensional measurements and multi-dimensional measurements. Alright folks, if you're ready for this lecture, so am I. Let's get started. Okay, so let's start with projections. What are projections and how do they work? Let's get started with a small review. Recall that the inner product of a quantum state with itself is just 1. Why is that? Well, what is the definition of a quantum state? A quantum state is just via postulate 1 of superposition. The quantum state can be written as a linear combination of some basis vectors j weighted with some coefficient alpha sub j, and we sum across all these basis vectors. So what is this saying? This is just saying the principle of superposition. Namely, if you're in 2 dimensions, then you have alpha 0 plus beta 1 in the computational basis. Computational basis just means we're in the basis vector 0 and 1. Folks, you might be wondering what a piano is doing in the middle of a math lecture. This musical interlude was designed to prevent you from falling asleep. Now that I've done my job, let's head back to the chalkboard. See you there. So, these vectors 0 and 1 define a Hilbert space, which we discussed in the first lecture. If you don't understand what my jargon is, well, go ahead, check out the first lecture, and then hopefully you'll be better accustomed to it, or you can just ask any questions you have in the comments down below. So now we know that a quantum state is defined as the linear combination of some basis vectors weighted by some amplitude, right? And to find the probability of finding the quantum system in that state, we can simply find the magnitude of that amplitude, right? We can simply find the magnitude of alpha sub j and square that to get the probability of finding the quantum system in this state. Right? We saw that in lecture 1. You can go ahead and check it out again if you feel uncomfortable with the material. So that is the basics we need for this lecture on measurements and projections. So now, if we have an inner product of a state with itself, we get 1. But what if we have something called an outer product? Let me show you what an outer product looks like. What if I have something like this? This is a ket vector, right? It's just waiting for a bra like this to come along and turn it into a scalar, a number. But what if instead of giving this guy a bra, I come along with a ket, another ket? So here's another ket. What is this? What does this even mean? Right? I know what this is. The inner product of a quantum system with itself, a quantum state with itself, is just 1. But what is this? What happens instead of doing a bra and a cat, what if you do a cat and a bra? What are you going to get? Well, this is what projections is here to answer. What you're doing right here is creating a projection. Let me show you what that means. So, I think it's best that we begin with a picture. In the computational basis, we have two vectors. We have the up vector, which is 0, and we have the horizontal vector, which is 1. I know my up vector is a bit slanted, but hopefully you get the point. Now let's say I have some vector, some quantum system, and that system is in some superposition of two quantum states, 0 and 1. Let's call this ket psi. Now, ket psi can be expressed as a linear combination of 0 and 1. But how do I know what the combination is? Well, I can simply project ket psi onto the 0 vector and see how much it's pointing in that direction. So, when I project ket psi onto the 0 vector, I'm going to get some vector over here. I'm going to get some vector over here that lies along that 0 axis. And what is that vector? That vector is simply the projection of ket psi onto the 0 state. That's how we write that. The projection of ket psi onto the 0 state. Onto the 0 state. So this right here, you can also write it as the projection on the 0 state of ket psi. And say we want to project ket psi onto the 1 state. How do we do that? Well, simply do the same thing. Project it onto the 1 state, and it's going to hit the 1 state at some position. That's going to be over here. And we write that as 1, the ket 1, bra 1, and then ket psi. So this is simply the projection onto the 1 state of the quantum system ket psi. Okay? So that's all projections are saying. And to write this in a more abstract way, we can project a quantum system psi onto an arbitrary quantum state k. And that's how we would write that. Furthermore, recall that ket psi is simply a combination, a linear combination of some weighted basis vectors. Right? And so when we take the inner product of ket psi with itself, we should get 1. And indeed, that's what you can see. How can we see that? Well, if I take the adjoint of this and apply it, I'm going to get 1. But here, when I have an outer product, this right here is known as an outer product instead of an inner product. An outer product doesn't give me a scalar, it gives me a projection, right? I'm projecting this quantum system into this state or that state. And a feature of projections, a very important feature of projections, is that repeating a projection gives you the same result. If I project ket psi onto the 0 state and then project it again into the 0 state, I'm going to get the same vector, right? Another way to say that is the square of some projection is equal to the projection itself. In fact, the nth exponent of the projection is equal to the projection itself. And how can we verify that? Well, we can take the outer product of k, ket k, and bra k, and square it. What am I going to get? Well, I'm going to get ket k, bra k, and then repeat this, right? Ket k, bra k. And what do I have here? Well, this is simply the inner product of k with itself, and that is simply 1. And here I just simply have ket k and ket k again. Ket k and bra k, sorry. And so ket k bra k whole squared is simply equal to ket k bra k. That tells you that the square of a projection is the same as the projection itself, which makes sense. You project the ket psi onto the 0 state, you get the whatever this projection is, and then project this projected vector onto the 0 state again, you should get the same thing, right? A shadow is the same shadow. Okay, so that's it for this section. Now let's dive into some examples of projections. Boom! I'm back just so you don't fall asleep. Let's go ahead and take a look at projections. So, an example of projections is very simple. Let's say we have two vectors, okay? The inner product of these is, of course, 1. And why is that? Well, I can use instead of Dirac notation, if I use vector notation, maybe it'll be more clear to you. This right here is a ket. It represents a column. And in a certain basis set, let's say we're in the basis set 0, 1, 2, 3. In that basis set, the vector ket2 looks like this. Here is 0, here is 1, here is 2, here is 3. And the vector bra2 looks like this. It looks like 0, 1, 2, 0. Take their dot product, which is exactly what an inner product is. You get 0 times 0 is 0, 0 times 0 is 1, 1 times 1 is 1, 0 times 0 is 0, giving you a total sum of 1. That's why the inner product is 1. Why is the outer product a projection? Well, let's take a look at the vector form. This right here is a row. It's a ket. Sorry, it's a bra, which is a row. So you have something like this. 0, 1, 2, 3. And here, this ket is a column. So you have 0, 1, 2, 3. And when I multiply these, I'm no longer going to get a scalar. Why is that? Well, look at what we have here. Here I have one row with 4 columns and 4 rows with 1 column, which gives you a total of 1 by 1 matrix, which is just a scalar. Here, however, I have 4 rows by 1 column and 1 row by 4 columns, which should give me a 4 by 4 matrix, right? Taking the first and last entry's dimensions. So what is my 4 by 4 matrix going to be? Well, you can painstakingly work through the 16 dot products, or alternatively you can think, hey, I want 0 of the first column, so that's going to be all zeros. I want 0 of the next column. I want 1 for the third column. And I want 0 for the last column. And hence, this is the matrix I have. This right here is the projection 2 matrix. So that right there is an example of why inner products give you scalars, outer products give you these crazy matrices. And what do these matrices do? They project a vector onto one of the basis. They project a quantum system into one of its basis states. And that's what you're looking at right here. This is a matrix that does that transformation of taking, as we saw, of taking a vector ket psi and projecting it onto either its 0 basis state or its 1 basis state. Okay, so now let's go ahead and take a look at a more sophisticated example of projections. All right, so now let's take a look at a more sophisticated example of projections. So let's say we have a quantum system ket psi that's in a superposition of the 0 state and the 1 state. In particular, it's in a superposition of this much of the 0 state and this much of the 1 state. And if you want, you can confirm that the probability that the system is in the 0th state, which is simply the amplitude squared of the coefficient, and the probability that the system is in the 1 state, which is again the amplitude squared of this coefficient, these probabilities sum up to 1, as they should, right? So these are equal to 1. So we know we're working with a valid normalized quantum system with orthonormal states. Orthonormal simply means that the 0th state is orthogonal or perpendicular to the 1 state, and the two basis vectors are also normalized, meaning their length is 1. So now let's go ahead and see what the goal of this problem is. The goal of this problem is to use projections to turn this quantum system from the computational basis, which uses the 0 and 1 states, to the plus minus basis, which uses the plus minus states, as you might have guessed. So how are we going to make a change of bases using projections? Well, first let's see how much our system points in either direction. To see how much our quantum system points in the 0 direction, we simply use the 0 projection outer product. And to see how much our quantum system points in the 1 direction, we simply use the 1 ket 1 bra outer product. And we're going to execute this outer product on ket psi, execute this outer product on ket psi. What does this give us? Well, this is 0, 0. Plug in ket psi as root 3 over 2, 0 plus 1/2, 1. And likewise, this is going to be 1, the outer product of 1, and root 3 over 2, 0 plus 1. Oh, I forgot to put half 1 instead of 1. Otherwise, the state would not be normalized. So we have half 1. Okay, so now let's go ahead and execute the arithmetic here. Here we're going to be left over with 0. Whoops. First put the coefficient, root 3 over 2. Just distribute as you would with numbers. So we'll have the outer product of 0, and here we have an inner product of this 0 with this 0. So ket 0 and bra 0 and ket 0 meet up to make a scalar, plus half, and then bring this outer product right here and put the ket 1 right here. Well, we know what the inner product of a vector with itself is. It's just 1. So this is just 1. And the inner product of two orthogonal vectors, or two orthogonal states, is simply 0. So what are we going to be left with? This is simply going to equal root 3 over 2 ket 0, right? Since this ket 0 is the only thing left over, as well as this coefficient of root 3 over 2. Now let's do the same arithmetic with our second projection. Here we have the projection of our quantum system onto the 1 state. So we have root 3 over 2 times the outer product of 1 with itself, 0, plus half the outer product of 1, and then this ket 1. Notice that these two states are orthogonal. 1 is orthogonal to 0. Check the picture right here. They're 90 degrees to each other, perpendicular. And so their inner product would be 0, as in here. And since the 1 vector is also normalized, the inner product of a vector with itself is simply 1. So this whole thing goes to 0, and we're left over with only this term, which is half of the 1 state. So we can write that here. Half of the 1 state. And guess what? Adding up these two projections simply gives you the original state vector, right? The original system. Root 3 over 2 times the 0 state, and half of the 1 state. This is simply the original ket psi, right? So what did we learn? Well, we just learned that using projections really does work. Projecting a system into one of its basis vectors simply gives you the coefficient times that basis vector, and projecting onto the other basis vector gives you the basis vector times however much your quantum system is pointing in that state. So that's exactly what we've confirmed via this approach. Now we're going to see how much our quantum system points in the plus direction and the minus direction. The plus direction being this direction and the minus direction being this diagonal. So let's go ahead and see. Check it out. Okay, so we're going to start by projecting the quantum system onto the plus state. So let's go ahead and do that with the outer product of the plus, execute it onto the quantum system ket psi, and let's see what we're going to get. Recall that ket psi, I'm going to write it right here, is simply the 0 state plus the 1 state normalized by a factor of root 2. So let's go ahead and execute this. We're going to have, and before I do that, it's worth remembering, before I do that, let's see what is ket plus with, bra plus with 0 and bra plus with 1. What are these two going to be equal to? Before we execute this computation, it's worthwhile to know what these two inner products are. Well, bra plus is simply 0 ket and 0 ket 1 normalized times ket 0, and here we have bra plus again, but instead we're taking the inner product of bra plus with ket 1 instead of ket 0. Well, here what do we have? Well, first of all, you have to remember this is not bra plus, this is ket plus. We've got to take the adjoint of this to actually take the inner product with 0. So taking the adjoint simply flips these kets into bras, and we have the 0 vector here. Likewise, flip the cats into bras, and we have the 1 vector here. Now, what do we have left over? Let's see, for plus, the inner product of plus and 0, we have bracket 0, 0 plus bracket 1, 0 normalized by a factor of root 2. Well, inner product of a vector with itself, simply 1, and an inner product of two perpendicular orthogonal states is 0. So we're simply going to be left over with 1 over root 2 for the inner product of plus and 0. How about for the inner product of plus and 1? Well, let's see. For plus and 1, I'm going to have, doesn't seem like I have much space left, but I'm going to have plus 1, and this is going to be the inner product of 0 and 1, and the inner product of 1 and 1, normalized. Well, the inner product of two orthogonal vectors is simply 0, and two same vectors, their inner product is simply 1. So I'm left over with, once again, 1 over root 2, right? So, moral of the story is I can just look at the coefficients of the plus vector to see how much it points in the 0 or the 1 state. Here the coefficient with 0 state is simply 1 over root 2. Coefficient with the 1 state is simply, again, 1 over root 2. Hence, the inner products of both of them being 1 over root 2. So let me go ahead and erase these. Okay, so all of that math and direct notation was simply to say that the inner product of the plus state with the 0 state is 1 over root 2, and the inner product of the plus state with the 1 state is also 1 over root 2. So now let's execute this computation. I have the outer product of plus with my quantum system, which is root 3 over 2 times 0 plus a half times 1. So I'm going to have, expand this out, distribute as you would in algebra. So I'll have the coefficient of the first quantum state times the outer product, of the plus state with the 0 vector here, and the outer product of the plus state with the 1 vector here. Okay, well, I know what the inner product of the plus state with the 0 state is. It's simply 1 over root 2. So this is simply 1 over root 2. Likewise, for the inner product of the plus state with the 1 vector, it's also 1 over root 2. So I have root 3 over 2 times 1 over root 2 gives me root 3 over 2 root 2 for the plus state, and 1 over root 2 times 1 over 2, simply 1 over 2 root 2, again, the plus state. And so my quantum system points in 1 plus root 3 over 2 root 2 in the plus state. All right, great. And now let's repeat for the minus state. For the minus state, all we need to change is the inner products, right? The inner product of the minus state with 0, well, look at what the minus state is. The minus state, I was looking here, but the minus state is simply the difference of the 0 vector with the 1 vector. So that means the inner product with 0 would stay the same, but the inner product with 1 would just have a minus sign now. So that means, let's go ahead and erase. So the inner product of minus with the 0 state is 1 over root 2, minus, with the 1 state is minus 1 over root 2. And why is it minus 1 over root 2? Well, the coefficient of the minus state for the 1 vector is minus 1 over root 2, which is why we have that here. You can do the inner product out and see you arrive at that. Now, let's go ahead and do the math. So let me actually erase this nicely so that you don't have streaks of white all over the board. So what are we going to have? Well, let's expand it out. We have the outer product of minus times the quantum system, root 3 over 2, 0, plus 1 half 1. And so what is this going to be? Well, just distribute as always, root 3 over 2, and then the outer product of minus with 0, and then plus half times the outer product of minus with 1. And we know what the outer product of minus with 0 is. It's simply 1 over root 2. And the outer product of minus with 1 is minus 1 over root 2. And so 1 over root 2 times root 3 over 2 is going to give me root 3 over 2 root 2 times the minus state, and minus 1 over 2 root 2 of the minus state. And so I have root 3 minus 1 plus root 3 over 2 root 2 of the minus state. That's how much this ket psi, this quantum state, this quantum system points in the minus state. So now, finally, I can write the answer for this problem, which is as follows. The quantum system, ket psi, can be rewritten as a linear combination of the plus state, this much of the plus state, root 3 plus 1 over 2 root 2 of the plus state, and this much of the minus state, root 3 minus 1 over 2 root 2 of the minus state. This right here is our final answer. Voila! Alright folks, and now the last example we're going to do for projections is understanding why the projection operators have to be orthonormal. In particular, why do they have to be orthogonal? For example, why can you have but not projection operators like this? Why can't you have projection operators like this, but you can have something like this? Well, here the 1 and 2 states are orthogonal. But here clearly the 0 state is not orthogonal to this state because this state already contains the 0 state, right? So this is not orthogonal. Hence this cannot be a good projection operator. But of course, there are those who like to challenge the convention, and they'll say, you know what, I'm going to be a rebel. I'm going to choose to use this projection operator and not this projection operator. After all, what's the worst that can happen? Well, we'll check that out in this example. Say we have a quantum system, ket psi, and it's in a superposition of a few states, of 3 states actually, the 0 state, the 1 state, and the 2 state. I just put this minus sign here because I want to. If you want to put a plus sign, it's not going to change the answer. And we're going to normalize it by dividing it by root 3, so that the probabilities for finding the system in each of these states is 1/3, the square of the amplitude of the coefficient. So we're going to project this quantum system onto this set of basis vectors, 1 and 1 plus 2 normalized. So if we have these two vectors, these two states for our projection, what are our projection operators going to be? Well, our first projection operator is going to be 1, 1. So the outer product of 1 with 1. And our second projection operator is going to be this, and then the adjoint of that state. Right, so 1 plus 2 over root 2. And then the adjoint of that state, which just changes the ket sign across, since we have no imaginary components. Recall that the adjoint is nothing more than taking, for example, if I have alpha ket psi, the adjoint of this would be the complex conjugate of alpha times, instead of a ket psi, a bra psi. Okay, so that's just a quick refresher of what the adjoint does. This right here is the definition of the adjoint operator. So let's expand this out, see what's the worst that can happen. So I'll have the outer product of 1 and 1 plus, just distribute as usual. So I'll have 1, 1, 2, 2, 1, 2, 2. So the outer product of 1 and 1, outer product of 1 and 2, outer product of 2 and 1, and outer product of 2 and 2. Okay, so this is our entire projection operator, just adding up these two outer products. And now let's apply our projection operator to this little nugget of a system. Let's see what we get. So I'm going to apply our projection operator to ket psi. What do we get? Let's see. The outer product of 1 and 1 plus this jumble. And by the way, at this point I should note that it is not good to expand these kinds of things out, because at the end of the day, you're going to have bras and kets matching to bras and kets. So writing it out in this expanded notation really just increases your workload. Not necessary. Let's go back to this distributive, pre-distributive notation. Okay, let me make this a bracket. So here I'll have 1, 2, and 1, 2. Normalize, normalize. And we're going to project all of this onto this state. What is our state? It is ket 0, ket 1, ket 2, plus minus, normalize. And now let's see what we get when we apply this projection operator onto this quantum system. I'm going to have first this outer product applied here. The ket 1 is going to destroy this, leave only this, leaving ket 1 over root 3 over here. So we'll have, again, what I'm doing is I'm just applying this bra 1 to this ket 0, that's a 0, bra 1 to ket 2, that's a 0, bra 1 to ket 1, that's a 1. So I'm going to have 1 times ket 1, which is ket 1 over root 3. So I'll have ket 1 over root 3 after applying this part of the projection operator. Now the second part of the projection operator, here it comes. So apply bra 1 to this ket 0, that's a 0, bra 1 to this ket 1, that's a 1, and bra 1 to this ket 2, that's a 0. So I'm going to have a 1 from this side, and then when I apply 2, I'll have a minus 1 from that side, right? So, seems kind of weird. Let's do it out then. So that is not for keeps it. Do it. Okay, everything that has different states is 0 because of orthogonality. Orthogonal states have an inner product of 0. So these are 0. And the same states, if you take the inner product of a state with itself, then the inner product is just 1. This is just 1. So I have 1 minus 1 over root 6. Doesn't leave me with anything. So that means my final projection of ket psi onto this space is ket 1 over root 3. Okay, so seems like everything is pretty okay. What's so bad about this projection operator right here? Well, what's bad is that if I actually square this projection operator, it's going to give me a different result. That means if I apply this projection to the state again after I've already projected it, I'm going to get a different answer. So, in summation, p squared is not equal to p. And that's bad. That violates the fundamental idea that projection, if you repeat it multiple times, it's going to give you the same thing. Idempotency. When you do the same operation, idempotency is the idea that if you do the same operation multiple times, it's not going to affect the final answer. So again, a shadow is still the shadow. If I project a vector, ket psi, onto, for example, the 1 state, I'll get this projected vector. And if I project it again onto the 1 state, I'll get the same vector. It doesn't make a difference, right? P squared ket psi should be the same as p ket psi, right? But in this case, that is not true. This projection operator squared is not the same projection. And in fact, we can generalize this. Let me generalize this, that a projection is some outer product. I'll say ket psi and bra psi, so that a projection squared is simply, if I square this projection operator, I'll just be squaring this entire thing. Whoops, not to the power of k, squared. So if I square that, what will I get? I get this outer product, k psi sub k, and I'll have the same thing but now with j. So outer product right there. Now let me combine these two so that the projection squared is simply the summation over jk. I'll have ket psi sub k and this inner product of ket k with psi psi sub j, and then I'll have one more psi sub j waiting out here. Now, if these two basis vectors are orthonormal, then this right here is simply the Kronecker delta, right? I believe we discussed the Kronecker delta in the first lecture, but just to refresh your memory, the Kronecker delta is a function that gives you 1 if j equals k and 0 if j is not equal to k, right? So if these two guys are equal, then j would be equal to k, and so you'd be left with none other than just the summation over k of the outer product of ket psi k and bra psi k. And what do you know? That right there is the initial projection. So that means the projection squared is equal to the initial projection if and only if the basis vectors, the projection vectors, are orthonormal. Most importantly, orthogonal. All right, folks, that's it for this episode of quantum computing. I hope you've learned a lot. In this episode, we discussed measurements, we discussed projection operators and why they have to be orthogonal. We even did a proof of, well, a kind of qualitative proof, if you will, of what happens if the projection operators are not orthogonal. All right, folks, if you have any questions, concerns, any comments or feedback, leave them down in the comments below, and I'll see you in lecture 3.